Well, here we are, balancing a reaction using RedOx. And here's the equation: magnesium, which is a metal, nitrate, which is acidified. You've got this hydrogen ion, so it's nitric acid that you're using. Nitric acid is one of the strong acids and completely 100% ionizes. In an acid solution, nitrates tend to be quite nasty, oxidizing agents. So it'll attack the magnesium, turn it into magnesium plus 2. We've got some leftover ammonium. This has got to be a dilute solution because nitric acid can change into quite a few other things. Some of them are quite nasty. If you use concentrated nitric acid, you'll get brown fumes, which are poisonous, nitrogen oxides, and of course water. But before we try balancing this reaction using RedOx, let's look at some of these materials. They're interesting. Magnesium is a metal. It's a bit more expensive than aluminum, but it's a lot less dense than aluminum is. In fact, one of the things about magnesium is that it has this very low density and it's still a pretty strong metal. If you can afford it and not worried about the fire hazard, because magnesium can burn, it's used in things like ladders where you need some strength, but you want to have a lot of light weight. And also, it's used quite often in airplane manufacturing. Here you can buy some cubes. This is a 1.5-inch cube of magnesium. It only has a mass of 95 grams. If this was aluminum, it'd weigh almost twice as much. It would weigh 150 grams. And the reason this company, Midwest Tungsten, sells these cubes is just that these cubes are just amazing. You grab this magnesium cube and you expect it to be heavy, and as I say, it's half as dense as aluminum, so it weighs about half as much as you could possibly expect it to. Contrast that to the tungsten, which is over here. The reason they sell tungsten is because it's one of the densest substances with a density of 19 compared to magnesium's 1.7 and aluminum 2.7. As I said, the magnesium cube will weigh about 95 grams, but this tungsten cube will weigh 1,000. You grab it, and you I can't lift this. And that's why they sell these cubes just as sort of novelty items. So magnesium, one of the lowest density metals that you can use for practical purposes. So that was our magnesium as the metal, but in the reaction, the metals reacted with the nitrate to make magnesium ions. And just as magnesium is pretty notorious for having its low density, the magnesium ions are notorious for being a laxative. In fact, if somebody needs to be cleaned out very quickly, they sell these bottles with about 0.3 molar magnesium citrate. The citrate ion is non-toxic and has sort of a sour sweet taste and is very soluble. So that's why they use the citrate as the anion for magnesium. So here you go, magnesium citrate, the laxative. So our reaction is changing metal to a ion that is soluble. Nitric acid, nitrate, and H plus, because you're not going to find HNO3 in a solution because this 100% ionizes. Even though you can buy very concentrated nitric acid and it's called HNO3, we know that it ionizes, so it's hydrogen ions and nitrates. One of the notable things about nitric acid, it's one of the most dangerous acids that you can have in a lab. In fact, you have to sort separately. In fact, that's what they're selling here for 150 bucks, is this small container that is made of a relatively inert substance, but even then nitric acid attacks it slightly. The nitric acid should be stored separately from any other substances because it's such a strong oxidizing agent. Notice it has this red cap. Typically by the end of the year, this cap will be corroded because of the nitric acid's action. Usually the solutions will be yellow tinged because they tend to decompose into nitrogen oxides, which are fumes and typically yellow. Notably, in terms of storage, there was a case where a flight crashed because some nitric acid bottles were not properly packaged and they started to oxidize their packing material, and the plane was filled with this smoke and crashed as a result. So if you're going to work with nitric acid, make sure you get a little bit of training ahead of time to warn you about its hazards. So back to our equation here, we know we've got a metal, we've got an acid, and it produces a ion solution. And here's some ammonium ions. Nothing really special about that. But let's get on to balancing, which is probably why you came to the site. How do I balance this thing? Well, with oxidation reduction reactions, you have to determine the oxidation numbers of the substances that are reacting. Elements are really easy. Their oxidation numbers are zero. You find an element all by itself. There it is, element, Mg, zero. And you know also it's going to change because if it's a reaction, it's not going to be a metal all by itself in the products. So let's see what happens to the magnesium if it goes from zero to what's it here? Well, +2, because when you have a ion, simple ion, its oxidation number is the same as its charge. So we have our magnesium going from Mg to Mg +2. The numbers going up, that's loss of electrons, that is oxidation. We're going to be dealing with a oxidation and reduction. In this case, we'll know our magnesium changes into magnesium +2. And that magnesium +2, the only way you can go from a 0 to a +2 is to lose some minuses. Chemistry is all about moving electrons. In this case, the electrons have to be removed from the magnesium, so we lose 2 electrons. That's our oxidation, loss of electrons. You've got half this oxidation and reduction taken care of already. Nitrate is notorious for a substance that will reduce. It's the oxidizing agent. And let's go quickly to our outline. Here's my outline that talks about oxidizing agents and numbers and oxidation reduction. The nitrate, the chromates, the permanganates are notorious for being able to, in a reaction, reduce. They start off with a very high oxidation number, +5. So that's not going to go up. It's going to go down typically, hence reduce by gaining electrons. Chromate's the other notorious one, and so is manganese. These are worth memorizing. Get some flashcards before the exam, and they'll save you a couple of seconds so you won't have to calculate their charges. If you want a mnemonic, you can use the AP periodic table and say, okay, nitrogen 5, chromium 6, manganese 7. There's a little bit of chemistry in there, but really it's more of a mnemonic than an explanation. So back to our problem, because we're ready to take care of the nitrate as our next substance. So let's say you couldn't remember the charge of nitrogen and nitrate. Then you'd have to calculate it. And when you have to calculate it, you've got to go by what you know. We know the oxygen is going to be a -2. It's always a -2 unless it's a peroxide or it's attached to fluorine. But we have 3 of them. So if you're going to be dealing with a -6. And this nitrate has a charge of -1. And in order to get a -1, the nitrogen is going to have to be a +5. So by logic, -2 times 3 gives us -6. The ion has a charge of -1. Therefore, the oxidation number of nitrogen has got to be +5. Of course, if you have got a good memory, you had some flashcards and were prepping for the AP exam, you just put a +5 there and save yourself 15 seconds or a half minute, or also save yourself from possibly doing things wrong. So sometimes in a case of a test, it's worth memorizing these specifics. The nitrogen is a +5. And now we're going to have to find out what it is here as a product. Did it change? Most likely, because nitrates with a +5 tend to reduce. So you're going to have to use your knowledge of oxidation numbers to find out what the oxidation number of nitrogen is now. Well, hydrogen is a pretty reliable indicator. It's almost always a +1, of course, unless it's an element or in a hydride, but that's very unusual. And we have 4 of them. Let's see what 4 hydrogens is going to do. It's going to give us a +4. And with a +4 and a total charge of +1, we know then that the nitrogen has to be a -3. -3 and a +4 produce this +1 charge of the ammonium. There's only 1 nitrogen here. So that nitrogen's got to own those 3 extra electrons to become a -3. We have our nitrogen, starts off as a +5. It's got to reduce, it's got to pick up electrons to turn into a -3. A little tricky. Now we've got to go to 0, so we've got to pick up 5 electrons just to get to 0. And then to get the -3, you're going to need an extra 3. In other words, a total of 8. The nitrogen, these are a lot of electrons to pick up. It's a great oxidizing agent. Here it's going to take a lot of this magnesium and wipe it out, turning it into the magnesium ions. We've got our oxidation numbers. We have our 2 halves. That's all you need for a redox problem. But the other key to a redox problem is that we know the number of electrons lost equals the number of electrons gained. And that's not true here. Here you've got a 2, here you've got an 8. That can't be. We've got to pick up some more electrons. And the way we do that is knowing that we're going to have to take this entire equation and multiply it so that we get ourselves 8 electrons times 4. Now we spent quite a bit of time to get to this level, but this is it. You've pretty well figured out the balancing of this reaction. You need to have 4 times more magnesium than you have nitrogen. 1 mole of nitrate will react with 4 moles of magnesium. As they say, this nitric acid is nasty stuff. It'll wipe out 4 moles of magnesium. Don't spill it on some magnesium because it's going to react very, very quickly. It's exothermic. You get poisonous gases. No. Danger with nitric acid. We know that it's a 1 to 4. We can balance this thing. We can figure out what's here, because if we have 1 nitrate, then we must have 4 magnesiums. All of a sudden you got 2 coefficients. And of course, with 4 magnesiums here, you're going to have 4 magnesiums in our product already. And here's our 1 nitrate. Let's get our 1. And this is the heart of the reaction. Typically, this is where an AP question will stop. As soon as they realize that you figured out you need 4 times more magnesium than nitrate, that's usually the objective of the question. You pretty well answer it. But if you're compulsive and you want to do the rest of this thing, there are a couple of ways you can do this. You can see that here you've got coefficients in front of a +2 and a +1. And here you can balance the charges. So let's see. +4, a 4 times +2 is 8, 9. We've got a charge of +9. Already here we have a -1, so we'll need 10 hydrogens. You've balanced the reaction. Imagine a cube of magnesium being dumped into some dilute nitric acid, fizzing away, making a solution of magnesium ions. Look at this equation, 4, 1, 10, 4, 1, 3. But we came up with a logical way of figuring out how to balance redox and balancing reactions.